Hi everyone, so in this video we're going to take a look at how computers work electronically, just starting off from a very basic level. So in this diagram you can see a really simple electrical circuit. There's a cell here, a battery, which provides power, and the power goes through a mechanical switch which a person can turn on or off, and then the electricity will pass through this load. In this case it's a light bulb, so the electricity going through the light bulb will produce light, and then it will flow back to the cell. So this is a really simple type of electronics, and you might remember back at the start of the course we talked about the difference between two different types of electronics, analog and digital electronics. So we're going to be focusing in this video pretty much exclusively on digital electronics because that's what computers use. You might remember that in computers a signal is either a 0 or a 1. So if there's electricity flowing in a wire, we can say that's a 1. If there's no electricity, we can say that's a 0. And there's no in between, at least theoretically there's no in between. Adopting that very simple theoretical model is what helps to make digital electronics very resistant to error. So in the early days of electronics, circuits were simple like this, and they could do things like lighting bulbs, or maybe powering some other types of load, but what they could not do is make decisions, automatic decisions, perform automatic functions. And as electronics became a little bit more advanced, there were ways invented to allow circuits to do things in response to particular things occurring in the environment, for example timers, or things which would occur when electronics got wet so that they could sense moisture or something like that. But the real breakthrough for computers was the invention of the transistor, which happened I think sometime in the 1950s. So this, if I could move to the next slide, so this is an example of a transistor. This is a transistor that you could mount in a circuit. It's got 3 pins here, and the idea is that this is basically an electronic switch. The base, which is the middle pin here, is the on-off switch, and the other 2 pins are the input and the output which electricity flows through. So if you put this into a circuit and you connected one wire to the input, the number 1 here, and you connected the other wire to the 3, the collector, then electricity could flow through, provided that you put some electrical charge on the base, on number 2. Now if you remove that electrical charge, then electricity won't be able to flow from 1 to 3 anymore, and that disconnects the circuit. So being able to operate these switches with electrical charge means that you can use switches to operate other switches, and the ability to do that allows you to build really complex circuits which can start to make automatic decisions. If you look at a microprocessor example on the right here, these microprocessors are made up of thousands or millions of transistors. Even the very first microprocessors had probably about 5,000 transistors inside them. So these processors, the transistors inside, are much smaller than this one here. I mean, the transistor on the left is probably about as big as the tip of your finger or something like that, but the transistors inside a microchip are going to be tiny, and the smaller that they are, the more power efficient that they are, and also the faster that they can operate. So part of the reason that microchips have become so powerful is because we've got better and better at miniaturizing the transistors inside them. Okay, so let's think about how we can use transistors to control circuits, and if I move on a little bit, we can again, thinking about the transistor as a type of switch, see about how we can use those transistors to change the behavior of a circuit. So first of all, let's have a look at circuit 1. Now, each of these is a switch, and I've drawn them as mechanical switches there, but we could also think of these as transistors, so electrical switches which can be turned on or off by electricity. Now, supposing that electricity wants to flow through this circuit, and maybe it's connected to a light bulb or something like that, we can see that in this circuit, if switch A is open, then no electricity is going to flow because it can't get past A. And if switch B is open, then no electricity is going to flow because it can't get past B. If you want to get electricity to flow from the input to the output, then you've got to have both switches closed. So if we have, just move on to the, oh, sorry, gone too far. Okay, so if we want to analyze this behavior, we can see that if switch A and switch B are open, then that means that no electricity is going to flow through the circuit. So I'm going to actually edit this slide. I'm going to change the output to false. Okay, so what this means is that false here means that the switch is open, that it's not connected. And false B here means that this switch is not open, so it's not connected. And if neither of those switches are connected, I certainly won't get any electricity flowing through. So I record that as false in the output column. Okay, now how about if I closed switch A, but switch B was open? We'll just have a think about that for a moment. And hopefully you worked out that that will also not allow electricity to flow. So I'm going to put false because if I close switch A, but switch B is still open, it doesn't change the situation at all. I won't get any electricity there. And the same is true for the reverse. So if I open switch A but close switch B, well, that still isn't going to get electricity flowing through that wire. But in the last case, if I close switch A and I close switch B, then I am going to get electricity flowing through the wire. So what this allows me to do is, if A and B are transistors, it means that I can have two transistors and I can turn on a circuit only if the electrical signal into those two transistors, if both of those electrical signals are present. And we refer to this as an AND operation because what I'm saying is A and B both have to be true. They both have to have electrical charge on them in order for the current to flow in my circuit. Okay, so remember with the transistor, if the transistor is switched on, that means that current will flow. So if A and B are transistors, then A has to be true, it has to be on, B has to be true, and if they're both true, then electricity is going to flow through my circuit to the output. Okay, so now going back to this again, we saw that circuit 1 is an AND arrangement. Okay, A and B have to be true, and we call that an AND gate. I think the word gate is by analogy to a gate allowing things to go through. So this represents an AND gate in logic. So here A and B both need to be true. Let's look at circuit 2 and what do you think is the condition there? Okay, so we'll analyze circuit 2, and I'll just try to move forward again. This is not super responsive. There we go. Okay, so here's circuit 2, and in this case I'm going to again draw a table, and if I think about the situation where the switch A is open and the switch B is open, well, electricity can't get from the input to the output there, so that means I'm going to write false in this column. Okay. Now, how about if I close switch A, but switch B is still open? Well, that's not a problem this time, because the electricity can flow through switch A, and the fact that switch B is open doesn't actually cause any obstacle. So in this case, this output will be true. True meaning that the electricity flows. Okay, so this output is true. And the same is true in this case. So if A is open but B is closed, the electricity can flow through this side to the output, that is also true. And what if A and B are both closed? Well, in that case, it's also true that electricity can flow through. Okay, it's actually able to flow in both directions. So in this case, we've got mostly a case where electricity can flow through the circuit. The only situation where electricity can't flow is if both A and B are open. So if we compare that to the case before, this was called an AND gate because A and B must be true for the output to be true. This gate, on the other hand, you might be able to guess, is called an OR gate because A must be true, or B must be true, or both of them must be true in order for the output to be true. Okay, so we can see here that by using transistors in arrangements which allow us to create AND or OR gates, we can get electrical circuits to do things depending upon whether their inputs are true or false. So true means that electricity is flowing, and false means that it's not. Now, microprocessors are made up of lots and lots of these transistors, and it would be kind of painful to draw everything using these switch symbols. So we have an easier notation. What we normally do when designing circuits is we use this notation. Okay, so this is electrical notation for the AND gate, and I think it's easiest to remember it by comparing it to the head of the Android symbol here. If you don't know Android, that's a mobile operating system which is better than its main competition. In this case, we've got two inputs. Now that corresponds to the sorry, it's so slow to change the slide here. Okay, never mind, it doesn't want to change the slide. Okay, so it's got two inputs, and if we think about that table, we will get electricity flowing to the output only if there's electricity on input A and input B. Okay, so this is the same table that we drew earlier when we were looking at the switches in the AND configuration, but this time we're just drawing it using this symbol to help simplify our circuit diagram. Okay, so let's have a look at the next symbol. Now you might remember the AND gate, and the other gate was the OR gate. So let's have a look at the symbol for an OR gate. Okay, so a good way to remember this is to think of it as looking like an ORO. Okay, so in this case it's kind of curvy at the back and pointy at the front, and the truth table, this is where A or B must be true for the output to be true. So they don't both have to be true, just one of them has to be true for the output to be true. Okay, so those are the two logic gates we've looked at so far, and an OR. There's one other logic gate that I need to introduce you to, and this is a little bit different from the previous two because the two logic gates we've looked at so far, they both have two inputs. Okay, so in this case we've got input A and input B, and if A or B are true, the output will be true. But there is a logic gate which only has one input, so it's kind of the simplest logic gate, or one of the simplest logic gates. This is a NOT gate. Okay, and the thing that makes it a NOT gate is this circle on the end. It's useful to remember that because it does kind of look like a knot of string or something like that. And a NOT gate only has one input. And the way it works is that if there's electricity flowing to the input, you won't get any electricity on the output. And if there's no electricity flowing to the input, then you will get electricity flowing on the output. Okay, so it inverts that signal. It means that if you put a 1 on the input, you get 0 on the output. If you put 0 on the input, you get 1 on the output. So just to clarify there, if you're confused by talking about 0 and 1, remember that in computers, in digital electronics, false and 0 mean basically the same thing. They mean the absence of electricity on a wire. So no electricity, false, 0, they're all talking about the same thing. And electricity flowing or true or 1, those all mean the same thing. Okay, so when I'm drawing this truth table, I've put false here and true here, because when this is false, this is true. But I could equally well have put 0 here and 1 here, because 0 means no electricity flowing and 1 means there is electricity flowing. Okay, so we've had a look at these 3 logic gates, and, or, and not. Let's have a look at some examples, some example questions. Okay, can I get it to move on? My computer is really struggling with this application that ought to be simple. Okay, here we go. It's the miracle of JavaScript. So on to question. Oh no, it's gone too far. Let's try and go back. No, try again. Okay, sorry about that, guys. So, oh goodness gracious. Okay, so let's have a look at question 1 first of all. So maybe you can remember what these gates are. Just shout at the screen, what is this logic gate? Yes, that's right, it's an OR gate. Okay, and again shout at the screen, what is this logic gate? Yes, well done, it's an AND gate. So now I'm going to create a table to analyze what this circuit does. And the first thing I do is I could fill these all in with trues and falses, but because I'm a bit lazy, I'm going to use 0 and 1 instead of true and false. Now, the other good reason to use 0 and 1 is because you can do some binary counting to make sure that you get every possible row. So the first row, I'm going to call that row 0, and I write it out in binary, 0, 0, 0. And then the next row is row 1, so I write that in binary, 0, 0, 1. And then row 2, which in binary is 0, 1, 0. Then the next row, 0, 1, 1. I can see I haven't got enough rows, so 1, 0, 0 is row 4, 1, 0, 1 is row 5, 1, 1, 0 is row 6, and let's just add on another row. There we go. 1, 1, 1 is the final row, row 7. Okay, so now if we have a look at this circuit, I can see on this circuit that if A is 0, that means there's no electricity here, and B is 0, so no electricity here, then I'm not going to get electricity flowing out here, okay, because this is an OR gate. If A and B are both 0, that means I won't get anything flowing out of it. Now if C is 0 as well, then I've got 0 and 0 going into an AND gate, and if I look back at the table for AND, 0 and 0 is going to output 0, okay, or false and false is going to output false. So if I go back, that means that if everything is 0, the output will also be 0. I won't get any electricity out there. Okay, now I can actually shortcut some of this, because this AND gate, if I look back at the AND gate can only be true in the case where both of the inputs are true. Okay, so looking back at this circuit, I know first of all that if either of these inputs is not true, if either of them is 0 or false, then this output must be 0 or false. So that means that everywhere that C is 0, this output must be 0. So let's fill that in straight away, because C is 0 here, so that will be 0, 0, 0. Okay, if C is 1, the output might be 1, but I still don't know for sure, because C being 1 is not enough. I also need this wire here to be 1. Okay, so I need the electricity to be flowing on this wire here, and it can only be flowing on this wire here if one of these two wires has electricity flowing on it. So remember, this is an OR gate, and it will only allow electricity to flow here if one of these two wires has electricity flowing. So if I look here, well, even though C is 1, A and B are both 0, so that means there won't be any electricity here. That means there's nothing on the output. So I'll put a 0 here. Okay, now in this case, B is 1, which means that this will be 1, that electricity is flowing along here, and C is 1, so that means that both of these are true, or both of these inputs are 1, and it's going into an AND gate, which means the output will be 1. Now by the same logic, this one is also 1, and also in this case where A and B are both 1, that means this is 1, and the output is going to be 1. Okay, so when I analyze the circuit in question 1, this is the table that I come up with, okay, and this is called a truth table. It shows me all of the possible inputs and what output I will get for each of those possible inputs. Okay, so let's have a go at question 2 now. I'm just going to delete these outputs and we'll use the same table, but this time to analyze question 2. Now rather than me going through it straight away, please take a moment, draw out this table on a piece of paper or something like that, and see if you can decide what the output column should contain. Just pause the video for a couple of minutes and work it out yourself, and then play the video to check whether you got it right or not. Okay, so guys, here's the answer. So to analyze this circuit, I'm going to start off by looking at C again, because C is going to control whether this AND gate can output anything other than 0. If you remember, AND gates, they tend to output 0 or false in most cases. There's only one case where an AND gate could output 1 or true. So if I look back at this, I can see that if C is 1, it's going to go into a NOT gate, which means that this will be 0. And if this is 0, then the output must be 0. So everywhere that C is 1, the output must be 0. That means that all of these lines, because C is 1 here and here and here and here, then the output must be 0 on all of those rows of the table. Now if C is 0, then this NOT gate will change this into a 1, so this wire will be 1. And that means that whether I get an output or not depends completely on this wire. If this wire is 1, then the output will be 1. And if this wire is 0, the output will be 0. Now this wire comes from an AND gate, and the AND gate takes A and B as the inputs. So that means that this wire will only be 1 if A and B are both 1. Okay, so in that case, if A and B are not both 1, this is a 0. But in the special case where A and B are both 1 and C is 0, that's the only situation where this circuit will output a 1. Okay, so well done if you managed to get that table correct. If you didn't get it correct, don't worry, there's 2 more questions coming up, so you can redeem yourself. Okay, so let's move on to 2 more questions. So I think what I'll do is copy that table from the previous slide. And then paste it in here. Yep, works as well as expected. Let's try that again. Okay, there we go. So I delete the output. Okay, now guys, we've got a little bit of a complicated circuit this time. Okay, we've got 3 different inputs and we've got 3 different logic gates. So again, pause the video for just a second, draw yourself out one of these tables and see if you can work out what the output should be. Okay, so here we go with the answers. So first of all, if I have a look at this output, I can see that this wire here, if it's 0, then the output will be 0, and equally this wire here, if it's 0, the output will be 0. So I know that if A and B are both 0, this is going to be 0. So everywhere that A and B are both 0, which is in the first 2 rows, I know the output is 0. Now everywhere that B and C are 0, then I also know the output must be 0. So that is where B and C are 0. And okay, that only gives me one more row. Now I can notice that the wire B here is actually split so that it goes to both of the OR gates. So that means that if B is 1, both of these OR gates will output 1, and that means that the output is 1. So where B is 1, I can automatically say that the output will be 1. So that gives me almost all of my rows. The last row, I think I'm going to have to look at that a little bit more carefully. So I've got A is 1, I've got C is 1. That means that this must be 1 and this must be 1. So the output of the OR gates are both 1. And that means that the output will be 1 here. So there's my final answer. Well done if you got it right. If not, you've got one more question to go, so don't give up yet. Okay, so let's take a look at question number 4. So again, this one's a little bit more tricky. If you draw out the table and have a go at solving it yourself, pause the video and then come back to it in a minute or two and check whether you got it right. Okay, so let's go through this one. So again, we've got an AND gate on the end, but this time we've got an AND gate in the top left as well. So it's going to work a little bit differently. The first thing that I notice, I'm trying to look for easy patterns to simplify this. Well, I know that if A is 0 or B is 0, then this AND gate is going to output 0. And if this AND gate is going to output 0, then the final output is also going to be 0. So that means that everywhere that A or B is 0, the output must also be 0. And I can fill in a lot of rows on the table that way. So A is 0 there, A is 0 there, A is 0 there, A is 0 there, B is 0 there, B is 0 there. So it really just comes down to these last two rows on the table. So in both of these rows, A and B are both 1. And if A and B are both 1, then this wire between the two AND gates is going to be 1. And also this wire from the OR gate to the AND gate is going to be 1. So if both of those are 1, the output must be 1. So everywhere that A is 1, I know that the output is 1. Now, how does that make sense? Because I've messed up, because looking back at the previous gate, no, I'm sorry, I have done it right. I was just being a bit silly. Okay, so yeah, it can get a little bit tricky sometimes, and you can miss some details. So I hope I haven't actually made any mistakes in this video. If I have, I guess I'll go back and either put a note on it, or maybe I'll just remake it to avoid embarrassment. Okay, so there you go, guys. I hope that made sense to you. If not, then hop on the chat and ask me some questions, and maybe I can help to elucidate what I've said.